All right, let's dive right into the fascinating world of carboxylic acids. Today, it's all about one specific bond, just one, the one between the carbon and the hydroxyl group. Now, you might be thinking, what's the big deal about one little bond? Well, as we're about to see, breaking just that single bond is the key that unlocks a whole universe of new molecules and incredible transformations. Okay, so take a look at this. This is basically our roadmap for today. You see the carboxylic acid right there in the middle? That's our hub. And branching out from it are four different roads, four distinct chemical pathways. And guess what? They all start from the exact same place, breaking that carbon-oxygen bond. We're going to travel down each of these paths to make anhydrides, esters, acid chlorides, and amides, some seriously important molecules in organic chemistry. So let's start with our first path, making anhydrides. And the name anhydride kind of gives the game away, right? Anhydrous means without water, and that is exactly what's going on here. The idea is actually pretty simple. You take two identical carboxylic acid molecules. In this case, we're using ethanoic acid, and you basically force them to combine. How? Well, you add some heat and a really powerful dehydrating agent, something like concentrated sulfuric acid. Its whole job is to pull a water molecule out of the mix. Once that water is gone, the two leftover pieces get stitched together by an oxygen atom, and voila, you've just formed ethanoic anhydride. All right, let's head down path number 2. We're talking about making esters now. This process is called esterification, and it's a big one. Esters are the compounds famous for giving things like bananas and pineapples their amazing fruity smells. So yeah, they're super important, not just in the lab, but all over in nature and industry too. So this reaction is what we call an equilibrium. See those double arrows? That means it's a two-way street. It can go forwards and backwards. You've got your carboxylic acid and an alcohol on one side, and they react to make an ester and water. But to make sure we actually get the ester, we need to give the reaction a little nudge in the right direction. That's where a catalyst comes in, usually a strong mineral acid. It helps push everything forward, shifting that balance so we end up with more of the product we actually want. Okay, before we get into the nitty-gritty of how this happens, let's tackle this term, nucleophilic acyl substitution. I know it's a mouthful, but it's not so bad once you break it down. A nucleophile is just a molecule that loves to find a positive charge. The acyl group is the main chunk of our carboxylic acid. And substitution, well, that's just a swap. So our nucleophile, the alcohol, is going to attack that acyl group and swap places with the OH group that's already there. Simple as that. Okay, step 1. The acid catalyst we added donates a proton right onto the oxygen of the carbonyl group. Now, why does that matter? Well, think of it like putting a big flashing neon sign on the carbon atom that says attack here. It makes that carbon way more electron poor and way more attractive to our alcohol. So the alcohol's oxygen, which is rich in electrons, sees that sign and can't resist. It attacks the carbon, and for a moment, we get this temporary, unstable structure called a tetrahedral intermediate. Now, this next step is absolutely crucial. It's a little internal shuffle. A proton hops from the alcohol part that just joined over to one of the original hydroxyl groups. And this is a really clever chemical trick. You see, a plain old OH group, it just doesn't want to leave. It's what we call a poor leaving group. But by giving it that extra proton, we turn it into an OH2 plus group. And what does that look like? It's basically a water molecule that's ready to pop right off. We've just turned a terrible leaving group into a fantastic one. It's a classic move in organic chemistry. And here's the grand finale. That excellent leaving group we just made, the water molecule says, see ya, and takes off. As it leaves, the whole structure kind of collapses back down, and that carbon-oxygen double bond snaps back into place. For a split second, we have a protonated ester, but it quickly sheds that extra proton. And where does the proton go? Right back into the mix, ready to catalyze another reaction. And what are we left with? Our final ester product. All right, time for path number 3. This time, we're doing another swap. We're kicking out that hydroxyl group and replacing it with a super-reactive chlorine atom. This gives us something called an acid chloride. And these things are fantastic. They're like the power tools of organic synthesis, incredibly useful for building all sorts of other, more complex molecules. So, if you're a chemist and you want to make an acid chloride, you've got a few options in your toolbox. The 3 most common reagents are phosphorus pentachloride, phosphorus trichloride, and thionyl chloride. Now, they all get the job done. They all swap that OH for a chlorine. But as you can see from the reactions, they leave behind different byproducts. And that raises a really practical question, right? If you've got 3 ways to do the same thing, which one do you pick? I mean, in a real lab, you care about efficiency and purity. You don't want a messy cleanup. So it turns out one of these is the clear favorite among chemists. And the winner is thionyl chloride. But why? Well, it all comes down to its byproducts. When thionyl chloride does its thing, it produces sulfur dioxide and hydrogen chloride. And here's the brilliant part. Both of those are gases, so they literally just bubble away and disappear into the fume hood. What does that mean for the chemist? A much, much cleaner product and way less work trying to purify it. It's a beautifully elegant solution. Okay, on to our last journey for today, path number 4, making amides. Amides are another vital functional group. In fact, you're made of them. The peptide bonds that link all the amino acids together in proteins to build our bodies, yep, those are amide bonds. This reaction happens in 2 distinct stages. First, you get a classic acid-base reaction. The carboxylic acid does what acids do, and ammonia acts as a base. They react and form an intermediate salt, in this case, ammonium acetate. That's step 1. Then, for step 2, you just heat it up. The heat forces a water molecule to leave, and what you're left with is the final amide product, acetamide. And this 2-step logic isn't just for simple chain molecules. It applies perfectly to aromatic compounds too. You can see it right here with benzoic acid. It reacts with ammonia, first making the ammonium benzoate salt, then you add heat, a water molecule leaves, and you get benzamide. The principle, the core idea, is exactly the same. Now, let's level up a little bit. Take a look at phthalic acid. It's got 2 carboxylic acid groups, so what happens when you introduce ammonia? Well, you guessed it, it reacts with both of them to form an ammonium salt. And when you heat that up, it doesn't just lose 1 water molecule, it loses 2, and you end up with phthalimide, a molecule containing 2 amide groups. But wait, we can take this even 1 step further. If you take that phthalimide and really crank up the heat, something cool happens. The 2 amide groups, which are right next to each other, actually react, kicking out a molecule of ammonia. In doing so, the whole thing zips itself up into a stable, 5-membered ring structure known as phthalimide. Phew, okay, we have journeyed down 4 different chemical pathways, all starting from the very same bond. So now it's time to zoom out and put it all together. And here it is, our master map. This really drives home just how central the carboxylic acid is as a starting point. From that single COOH bond break, we've seen how we can make anhydrides, esters, those highly reactive acid chlorides, and amides. It's a powerful summary of how one functional group can be a gateway to so many others. So think about it. We've created 4 different types of molecules from one starting material. And that leaves us with a final question for you to ponder. Of these 4 derivatives, the anhydride, the ester, the acid chloride, and the amide, which one do you think is the most reactive, the most useful starting block for building even more complex molecules? That's a topic for another day. Thanks for watching.